তোমার বাড়িতে সবাই ভালো?
হ্যাঁ হ্যাঁ, সব ঠিক আছে।
না, এই সেকেন্ড ওয়েভটা খুবই ডেডলি ছিল, মানে তোমার সেকেন্ড ওয়েভ।
হ্যাঁ, এখানে একটা অনেক হয়েছে
এবার
এবং খুব
বাড়িতে
তাড়াতাড়ি ডিটোরিয়েট করে যাচ্ছিল।
সেটাই, সেটাই। এবার বাড়িতে এরকম দুর্ঘটনা ঘটে গেছে, তো তার জন্য আরো বেশি আর কি তোমার। আর আমার তাছাড়া আরেকটা ব্যাপার হচ্ছে, মানে আমাদের ঘরে ছোট ছেলে মেয়ে আছে, তো এবার তাদেরকে নিয়ে
হুম
tackle করাটা একটু মুশকিল আছে
হুম।
করোনা ভাইরাস করে। সেই জন্য এখানেই বসে আছি। এবার দেখা
হ্যাঁ
যাক, তখন পরিস্থিতি শান্ত হবে তখন বেরোবো।
হ্যাঁ, সেটা বটে। তোমাদের ওই প্রোগ্রামটা চলছে তো মোটামুটি ঠিকঠাক?
কোনটা
নাসি
কোনটা?
নাসি নাসি আর এস।
ওটা ওটা তো চলছে, হ্যাঁ, ওটা তো ওই
হ্যাঁ,
মানে এখানে ওই
আমার
ভাটিন্দা।
দু একটা ছাত্র আছে ওখানে
আচ্ছা আচ্ছা আচ্ছা, না আমি ওটা
করছে।
খুব একটা অ্যাটেন্ড করার সময় পাচ্ছি না, মানে
হ্যাঁ
আমার গত 2 সপ্তাহে মানে প্রচুর ব্যস্ততার মধ্যে কাটছে আর কি। মানে এরকম ধরো এই
হ্যাঁ
তোমাদের
হ্যাঁ হ্যাঁ
আরো একটা লেকচার ছিল, সেটা প্রিপারেশন একটু নিতে হয়েছিল।
হ্যাঁ, সেই।
তাছাড়া আমাদের মানে অফিসিয়াল ডিউটিও কিছু পড়ে গেছে আর কি।
হুম
তো সেই জন্য বিভিন্ন রকম ব্যাপারে আর ওটা অ্যাটেন্ড করার বেশি সময় পাচ্ছি না।
হুম।
তবে ভালোই চলছে আজকে। এখানে আসার আগে 1 ঘন্টা ওখানে আমি বসেছিলাম,
হ্যাঁ হ্যাঁ।
দেখলাম ভালোই হচ্ছে ওখানে।
হুম।
এই তোমাদের সিম্বা স্কুলটার কি খবর?
সিম্পা স্কুল তো এখন তো হবে বলছে, দেখা যাক জানুয়ারি মাসে।
ওটা কি ইন পার্সন হবে বলে মনে হচ্ছে?
আমি তো পিটারকে জিজ্ঞেস করলাম, বললো যে হ্যাঁ এখনো তো হওয়ার কথা।
আচ্ছা, ও অপটিমিস্টিক।
হ্যাঁ, সেই আমি বললাম যে একটু পিছিয়ে দেবে নাকি, বললো যে না, এখন যখন সিম্পা যখন বলেনি তখন থাক।
আচ্ছা, না তোমার সিম্পা স্কুলের দেখো, যদি মোটামুটি এখন যেরকম পরিস্থিতি সেরকম পরিস্থিতি থাকে,
হ্যাঁ
তাহলে ঠিক আছে। তাহলে
হ্যাঁ
তোমার
হ্যাঁ
সিম্পা স্কুলটা হয়তো ইন পার্সন করা গেলেও করা যেতে পারে।
হ্যাঁ হ্যাঁ।
হ্যাঁ, কিন্তু কিন্তু এখানে তো কিছু প্রেডিক্ট করা যাচ্ছে না।
না, যদি আবার হঠাৎ করে বেড়ে যায়, থার্ড ওয়েভ যদি এসে, তাহলে মুশকিল হয়ে যাবে।
বিশেষ করে আমাদের
হুম
যখন কলেজ স্কুল ইউনিভার্সিটি সব বন্ধ,
হুম।
এই অবস্থায় তোমার বিভিন্ন দেশের লোকজনদের নিয়ে সিম্পল স্কুল করাটা কতটা
সেই সেই হ্যাঁ
অ্যালাউড, মানে অ্যালাউ করবে অ্যাডমিনিস্ট্রেশন, সেটাও একটা প্রশ্ন।
হ্যাঁ।
তো দেখা যাক।
দেখা যাক আরেকটু, হ্যাঁ পুজোর সময় বোঝা যাবে।
হ্যাঁ,
অক্টোবর নভেম্বর নাগাদ বোঝা যাবে যে কি হবে।
যদি পুজো পেরিয়ে যাওয়ার পর এরকমই
হুম।
বুঝতে হবে যে ব্যাপারটা।
তাহলে হ্যাঁ, ঠিক আছে, হয়ে যাবে।
তোমাদের এখানে কেমন হচ্ছে মোটামুটি? কালকে তো ভালোই হলো আমি দেখলাম।
হ্যাঁ, এখানে তো ভালোই হয়েছে। মোটামুটি এটা 81 জন তো রেজিস্ট্রেশন করেছে।
আচ্ছা
আর 12 জন একটু আমাদের সিএমএস এ যারা এ করছে আর কি, ইন্টার্নশিপ করে, তো সিএমএস এ ইন্টার্নশিপ করছে 12 জন। তো ওরাও আছে আর কি, ওদেরকেও এ করা হয়েছে।
তো ইন্টার্নশিপে কি ধরনের জিনিসপত্র মানে করো?
ওদের কিছু কিছু কাজ দেওয়া হয়, ইন্টার্নশিপে কিছু কাজ দিয়ে, কিছু পড়িয়ে তারপরে কিছু কাজ টাজ দেওয়া হয়, সেগুলো করে। বিএসসি, ওরা বিএসসি স্টুডেন্ট যদিও।
বিএসসি স্টুডেন্ট ওরা
হ্যাঁ
বেসিক্যালি
হ্যাঁ,
আমার প্রজেক্ট টাইপের।
সামার প্রজেক্ট টাইপের, হ্যাঁ ঠিক। ওই অ্যামিটি ইউনিভার্সিটির ওরা
আচ্ছা,
ওখান থেকে এসছে, ওরা আছে কিছু।
আমাদের এখানেও একটা অ্যামিটি ইউনিভার্সিটি খুলছে আমাদের ইনস্টিটিউট থেকে, খুব একটা দূরে নয়। এখন ওরা ক্যাম্পাস তৈরি করেনি, কিন্তু
আচ্ছা
মানে
আচ্ছা।
করবার প্ল্যান করছে।
হুম। না, এখন তো প্রাইভেট ইউনিভার্সিটি গুলো আস্তে আস্তে ফ্লারিশ করছে।
হ্যাঁ, এখন প্রাইভেট
হুম।
ইউনিভার্সিটিতে প্রাইস করছে।
এটাই।
হ্যাঁ, তো তোমার মানে এই নর্থ ইন্ডিয়াতে তো অনেক প্রাইভেট ইউনিভার্সিটি হয়ে গেছে এখন।
দিল্লিতে তো অনেকগুলোই তো ভালো ভালোই চলছে।
আসলে পপুলেশন আমাদের এত বেশি যে তুমি একাডেমিক ইনস্টিটিউশন খুললে মানে
হ্যাঁ, চলবে ভালো।
যদি ঠিকঠাক লোকজন নেয়, তাহলে না চলার
হুম
কোনো কারণ নেই।
হুম হুম।
তো তুমি কি বাড়িতেই এখন না?
হ্যাঁ, না আমরা যাচ্ছি মাঝে মাঝে, এই শুক্রবার গেছিলাম, এই সপ্তাহটা আর যাবো না, আবার সোমবার যাবো, এরকম মানে সপ্তাহে 2-3 দিন যাচ্ছি আর কি। 2 দিন হয়তো সপ্তাহে।
না, আমিও ওরকমই, মানে আমাদের তো ক্যাম্পাসে
হুম।
তবুও আমি
হ্যাঁ হ্যাঁ।
একদিন আসতে হয় না। এই কালকে ওই পিটারের স্লাইড গুলো আমাকে পাঠিয়ে দিও তো, ইমেল।
হ্যাঁ হ্যাঁ, ও পাঠাবে তো বলেছে, ও পাঠিয়ে দিলে তো সবাইকেই পাঠিয়ে দেবে।
না কালকেও মোটামুটি একটা এনসাইক্লোপিডিয়া
পিঠা
হ্যাঁ
পাঠিয়ে
হ্যাঁ
দিয়েছেন?
পাঠিয়ে
পিঠা
দিয়েছেন?
পাঠিয়ে দিয়েছেন? আমি
আচ্ছা আচ্ছা,
পার্টিসিপেন্টও পাঠিয়ে দিচ্ছি। আমি ঠিক আছে, কৃষ্ণেন্দু বাবুকে পাঠিয়ে দিচ্ছি।
হ্যাঁ আমাকেও পাঠিয়ে দিন, হ্যাঁ সবাইকে
হ্যাঁ,
পাঠিয়ে দিন।
শিওর, পাঠিয়ে দিচ্ছি, আমি এখনই পাঠিয়ে দিচ্ছি।
হ্যাঁ মোটামুটি অনেকটা কভার করে
হ্যাঁ হ্যাঁ হ্যাঁ, আমি পাঠিয়ে দিচ্ছি।
হ্যাঁ। তো আসলে এখন
আমি আরো 2-3 মিনিট ওয়েট করবো।
আর একটু ওয়েট করো,
হ্যাঁ,
20
হ্যাঁ,
মিনিট।
হ্যাঁ।
হ্যাঁ,
আপনি ইন্ট্রোডিউস করিয়ে দিচ্ছেন তো?
তুমি কি রেডি করেছো কিছু? রেডি করে থাকলে
না
তাহলে
না, আমি রেডি করিনি না।
আচ্ছা ঠিক আছে ঠিক আছে, তাহলে আমি
হ্যাঁ, ওকে।
যে আমি কি আমার স্ক্রিনটা শেয়ার করে নেবো, মানে আবার দেখে নেবো শেয়ার হচ্ছে কিনা?
হ্যাঁ দেখতে পারো, দেখে না শেয়ার হয়ে যাবে।
প্রেজেন্ট
হুম,
দেখতে পাওয়া যাচ্ছে?
হ্যাঁ হ্যাঁ
না আমি তো কাউকে দেখতে পাচ্ছি না, আমি আরেকটা ডিভাইস থেকে লগ ইন করি।
আচ্ছা হ্যাঁ ঠিক আছে।
আচ্ছা, আমি পিটারের টকটা পাঠিয়ে দিয়েছি।
আচ্ছা আচ্ছা, থ্যাংক ইউ। হ্যাঁ
আচ্ছা ঠিক আছে না, মানে ওটিকো হচ্ছে না তো?
হ্যাঁ ঠিক আছে।
সাউন্ডটা কি এইখানে ভালো আসছে না এইটা ভালো আসছে? এইটা ভালো আসছে?
হ্যাঁ এইটাই সেকেন্ডটাই ভালো আসছে।
সাউন্ডটা বেশি ভালো আসছিল আগেরটা না এইটা?
না এইটাই ভালো আসছে।
হ্যালো,
হ্যাঁ এইটাই ভালো আসছে, এটা করো।
এই অরিন্দম দা শুনতে পাচ্ছ?
হ্যাঁ হ্যাঁ শুনতে পাচ্ছি, ঠিক আছে।
বলছি কোন সাউন্ডটা বেশি ভালো আসছিল, আগেরটা না এইটা?
না এটা ভালো হচ্ছে, এটা ভালো হচ্ছে, এটা দিয়ে
এইটা
বলো।
বেটার?
হ্যাঁ হ্যাঁ
এটা বেটার? আচ্ছা
এটা
তাহলে
better।
এটাই আমি রাখলাম। হ্যাঁ
ঠিক আছে ঠিক আছে।
ঠিক আছে ঠিক আছে।
স্টার্ট করি তাহলে, এবার স্টার্ট করি আস্তে আস্তে নাকি?
হ্যাঁ হ্যাঁ স্টার্ট করো।
41 হ্যাঁ।
ওকে।
ওকে আমার
So,
স্ক্রিনটা শেয়ার করাই আছে।
হ্যাঁ হ্যাঁ So good afternoon all of you. Today our first technical lecture will be given by Dr. Krishnendu Gongopadhyay, who is Associate Professor and Head of the Department of Mathematics, IISER Mohali. His research area is hyperbolic geometry, groups in geometry, and related topics. He has written many papers and books also on knot theory and on the other related topics. So I request Dr. Krishnendu Gongopadhyay to deliver his lecture. Krishnendu.
ওকে 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 So thank you, Arinanda, for this invitation, and thanks to all the members of Calcutta Mathematical Society for organizing this nice workshop and inviting me here. I would say that I am very happy coming to this workshop because I always heard about Calcutta Mathematical Society from
Dr.
the student.
Gongopadhyay, I beg your
Yeah.
pardon. Actually, your sound is not coming properly.
Oh, I see. Okay, just let me. Is it better now?
Yes, far better.
Okay, okay, great. Okay, so here my screen again. Okay, so just interrupt me if there is any problem in the sound quality or video quality. So I am saying that it is a pleasure that Calcutta Mathematical Society is organizing this workshop. I always heard about Calcutta Mathematical Society from my student life, and it is indeed a pleasure to take part in your workshop. So now the topic that I have been asked to speak, groups in geometry. Okay, so is there any question? Yes, and you can. Somebody has raised a hand. So anything?
Bishwajit Mitra, huh? Yes. Do you want to ask any question, Bishwajit, or any comment you want? Bishwajit?
Okay.
Okay, carry on. Huh?
Maybe it is just.
বিশ্বজিৎ কাকে কোন বিশ্বজিৎ
Bishwajit Mitra.
হ্যাঁ হ্যাঁ বলছি বলুন
বলো বলো।
হ্যাঁ
You
বলো
have
বলো আমি
raised-
শুনছি
You have raised the hand.
ও না 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 বাই মিস্টেক
Oh, acha, acha, okay, okay.
Okay.
ঠিক আছে,
Okay.
continue. হ্যাঁ।
কন্টিনিউ
Okay, so the topic that I have been asked to speak is groups in geometry. Now this is a very vast topic, and yesterday Professor Peter Isinski he has already given a broad view of groups, how they appear in geometry. Now you might have seen that in part of his lecture, he demonstrated the program of Gromov, where they consider groups as a geometric object. All right, so you take an abstract group and then you consider it as a geometric object, and then he defined quasimorphism and developed the theory. He presented some aspects of the theory. That is one aspect. But what I will speak is probably complementary to what he has spoken. So I think Peter has presented a very broad view of the entire scene of modern mathematics, where groups play a role in geometry. But here I will restrict myself to a more small domain from a classical viewpoint, but still it is sort of something that still there are lots of understanding that remains. And now we all know what are groups. So a group, the set G with a binary operation, and the operation which combines two elements, and it satisfies certain properties like it is associative. There is this unique element which is the identity element, and for every non-identity element in G, you have an inverse in G. So that's the basic definition of groups. And every time we learn the first definition of groups, the kind of sets that we have in mind are, they come from number systems. So we have the tendency.
Sorry, Dr. Gongopadhyay, may I interrupt you? Your sound quality was better first while you were testing. The first sound quality was better.
Okay,
So if you take a mic, it will be very nice for us.
Wait a minute. So let me.
Thank you.
You take that one.
The headphone, okay?
Yeah, it will be better.
Is it okay now?
Nice. It's perfect.
Yes.
Is it okay?
Yes, okay.
Something.
One sound is coming.
Okay. Right. So some sound is coming. Okay. Now it is okay, no? Still the sound is coming. Is it better now?
Yes. Now it is better. Okay. Again, a sound coming. So,
Okay. Is it okay?
yes.
Or maybe I. Okay. Okay. So, this sound is coming, right? Why it is coming that I just give you
Two sounds are on.
Give me 1 minute.
Just if you mute the other one, it will be better.
I mute the other one. Sorry.
Yes.
Now I think it is okay.
Yes, it is very nice and perfect. Yes.
Okay.
Now it is okay.
Thank you very much for your support in by giving feedback, because when I am lecturing in this online system, many times you don't know how others are receiving it. So, okay. So I have shared my screen, and this is the full screen mode. Okay. All right. So what I am saying that yesterday we have got a very nice viewpoint by Professor Peter Hysinski, who summarized how groups appear in geometry. Now today what we will do, we will see another viewpoint. So in Peter's talk, Peter did not say much about how algebraic structure of groups play a role in geometry. Now in this talk, I will do exactly that. I will demonstrate how algebraic structure of a group can contribute to the understanding of geometric objects. Now we start with basic definition of groups. So a group is a set with a binary operation, with the usual binary operation that you know. Now every time we define groups, the first example of groups that we have in mind come from the number systems, like the group of integers, real numbers, complex numbers, etc. But other than numbers, groups can also be viewed as symmetries. Now, what are symmetries in nature or in classical geometry? For that, you recall school geometry, the Euclidean geometry that we have learned in school. So there, two triangles or any two figures were said to be congruent if one could have been superimposed onto the other by using of certain kind of operations like rotations, translations, reflections, etc. So that means, like here, I have drawn three triangles. It's the same right angle triangle. So you rotate the first triangle or you reflect the triangle. Whatever you obtained, they are congruent to each other, right? Now, every time you want to superimpose one triangle onto the other, you have to apply certain kind of operations like rotations or translations along the plane, right? And you can just fit one triangle onto another and you say they are congruent, all right? So given a plane figure or given a figure in a space, I mean, you can ask that when it is congruent to itself and how many ways. Now, when you count the number of ways, that gives rise to symmetries of the given figure. Like here, I have demonstrated symmetries of a triangle. So groups can be realized as symmetries of these figures, and I will explain that more. But before I get into groups, I would like to request, especially the undergraduate and master student, that every time you read group theory, you remember that group represents symmetries in the nature. So groups are everywhere in the nature, and you have to look for them. For example, there are these crystals. I mean, I think in Bengal, many people wear these nice rings on their hands, right? So many people have 5-6 rings with nice crystals on the rings in their fingers. Now, each of those crystals, there is a chemical bond underlying each crystal, and there is a nice symmetry of the crystal. So it is an interesting exercise that if you are wearing a ring, you look at the stone on your hand and try to find out the symmetry in the stone. Then you look at the wallpaper symmetry. This already Peter explained yesterday, so I would not say much. But what I will say that we have our traditional artwork in Bengal, and they produce nice paintings on the wall. Now each of those paintings has hidden symmetries in it. Try to find that. So, and those symmetries will give you some group and find out the group which it represents. Now look at the flowers, like the one which I have given in front of you. This flower has 5 petals, and each of the 5 petals are symmetric to each other. So what does it mean? That means this center of the flower, if you fix that, then the petals can be thought of as congruent to each other by a nice symmetrical rotations around the center. And then you look at the decorations. We were discussing about Durga Puja. Now, on every festival in Bengal, there are decorations that people make. Now, this is one such decoration where you have 2 birds. One bird is looking in some way, and the other bird is taking something from the ground, but they are symmetric, and there is a symmetry that transforms one bird to the other. All right, so this way, whenever you look at something symmetric, be assured that there is a group underlying it. And this is essentially how groups arise in geometry. Now, to formalize that, we will recall Felix Klein, who Peter also recalled yesterday. So Klein proposed to view geometry as the study of properties of a space that is invariant under a given group of transformations. So that means you, instead of only drawing figures or talking about how curve is a figure, you can also view geometry as a study of properties of a space that is invariant under some group of symmetries which you can discover in that geometry. According to Klein, to study geometry, one needs not only objects like shapes in a plane, but you also have to look at the movements of the shapes. Now, in real life, we all travel by bus, right? And in Calcutta, I mean, I don't know what is the situation now, but when pandemic was not there, riding on a bus could have been a challenging task for any of us, right? Yeah, but people in Kolkata do that perfectly. And many times when you are squeezed yourself in the crowd in a bus, you don't see what is outside the bus. You only feel the movement of the bus, right? And by feeling the movement of the bus or the car, you can get an idea of the geometry of the road, isn't it? Like if there are many bumps, you can realize that, okay, this is a bumpy road. And you know, I mean, every time when you travel on a road, you get a feeling of how the road or the transport route can be just by looking at just by feeling the movement inside a bus or a car. So this is the same philosophy, that instead of looking at shapes, you also look how are the movements of a particular shape on the whole geometric plane or space, and then try to get an idea about the geometry of the underlying space. So this is the idea of Felix Klein's viewpoint. And how does the movements arise? The movement arise from symmetries, and symmetries arise from the underlying structure of the space we study. Now, to give an example, I will again go back to the example we learned at school, which is of the Euclidean plane. So what is the Euclidean plane? Because we all know coordinate geometry, you take the xy plane, which mathematically you can identify with R2, two copies of the Cartesian product of the real line, and then you define a distance like the one I have given. So R2 along with this distance can be an analytic model for Euclidean geometry, and we know that this distance comes from a inner product, which is a positive definite inner product. So to every vector on the plane, you can also associate a length of the vector, which is just the square root of the inner product of the vector with itself. And the distance between 2 points is essentially the norm of the difference of the 2 points. So this is how we define analytic model for Euclidean geometry in coordinate geometry. And we start with this. And then we can define an isometry of the Euclidean plane to be a bijection that preserves the distance. All right, and the set of all isometries of the Euclidean plane form a group. Now, since distance is preserved, shapes does not, at least shapes which are bounded by lines or objects which are invariant under the distance, they don't change. So shapes does not change under isometries in the Euclidean plane. Similarly, there is so we talk about concept of congruence. Now there is also concept of similarity. So you just take a triangle and you keep the angles as it is and stretch it. So that those two triangles are similar triangles. Now there are also similarity transformations that you can define in Euclidean geometry. But for the moment, let's talk about isometries only. So symmetries, so we will now consider these isometries as symmetries of the Euclidean plane. And these symmetries classically are known as rigid motions of the plane. And the transformation groups of isometries act on the Euclidean plane. Now recall what is a group action. So suppose I now again come back to an abstract group G and a set X. Now a group G acts on a set X if there is a function from G cross X to X such that these two properties are satisfied. That identity of the group maps each element to itself, and when you apply G on an element Hx, that is amounts to the same element when you apply GH, the product of G and H to X. So these two properties define a group action, and in geometry, groups play a role in geometry by this group action as well. So yesterday Peter thought of groups as geometric objects, but here what I am saying that you take a group and you take a geometric space. Now look at the action of the group on this space X, and then follow Klein's viewpoint. Look at how these elements of the group moves the points of X and try to get an idea about the geometry of X. Now here is a technical definition. An action of a group G on a set X is called transitive if for each xy in the set X you have an element G from capital G such that G maps small x to y. That means an action is transitive if, as long as the group action is considered, any two elements looks similar. That means there is no difference between any two elements as long as the viewpoint from the group is concerned. They look identical. So that's what transitiveness means. Now, look at the functions on a plane which preserves the inner product. So we have this Euclidean inner product. Let me again, this inner product xy. Now, look at the transformations which preserve this inner product. That means for all xy in R2, the inner product of phi x and phi y will be equal to the inner product of x and y. So such a transformation are called orthogonal transformations. Now the group of orthogonal transformations can be identified with a group of matrices. So you take all 2 by 2 matrices which satisfy this identity, A transpose equal to identity. Now you can see that these two notions, these two expressions, whether this element preserve the inner product or the corresponding matrix satisfies A transpose equal to identity, they are equivalent. And as soon as you define this transformation, you get this nice group O2, which is a group with two connected components. So you can think of O2 as a subset in R4, and you can give a topology on it. So under that topology, clearly O2 has two components. One component consists of determinant 1 matrices and the other component consists of determinant -1 matrices. And it follows from the definition or from the fact that it preserves the inner product that every element of O2 is also an Euclidean isometry. All right. Now the group of isometries where determinant is 1, we denote it by SO2, and it is the group of rotations of E2. We will see that. And when determinant of A is -1, it is also nice geometric transformation that we will see. Now I will say that this fact which I am explaining in detail, Peter also talked about it yesterday, but he just invested one slide on it. So I thought I will elaborate it further because I think this is essentially the main idea or the main philosophy which you can take as a prototype to understand how groups appear in geometry. Now, you take any orthogonal transformation by hand computation, you can find out using the relation A transpose equal to identity that A is either of these two forms. These nice matrices whose diagonal entries are cos theta and off diagonal entries are either minus sin theta or the other way around. Okay, diagonal entries are sort of negative to each other and off diagonal entries are same. Now look at the eigenvalues of the first matrix where determinant is 1. You can check that eigenvalues are e to the power plus minus I theta. So you can think of it, I mean, this acts as a rotation of the plane. And when determinant is minus 1, you can see that the eigenvalues are 1 and minus 1. So those are plane reflections. We will again see it, but here you can just choose your basis consisting of the eigenvectors. You will have these nice diagonal forms, either e to the power I theta, e to the power minus I theta, or 1 minus 1. And you look at its action on the plane, you will see that when determinant 1, they are just the rotations, and when determinant minus 1, they are reflections. We will repeat how you can see it in a different way in a few minutes. Now the theorem is that the orthogonal group acts transitively on the one-dimensional subspaces of R2. That means you take any line in the Euclidean plane, then the orthogonal transformations, they act transitively. And this is just easy to see. You can think of it as a baby version of the Gram-schemed orthonormalization process. It's a dimension 2 space, so it's very easy to prove. But I would say that it is actually a general fact, and if you replace 2 by any integer, positive integer, then the corresponding orthogonal group ON that acts transitively on the subspaces of the same dimension of higher affine spaces. Okay, but we will not give the detail of that statement. We will focus on the plane geometry at the moment. Now take any arbitrary isometry of the Euclidean plane. Then the theorem is that it is of the form phi of x equal to ax plus b, where a is the orthogonal transformation and b is the arbitrary vector from R2. And how to see that? So you start with any isometry, then define A to be the difference of that isometry, the translate of that isometry by negative of phi naught. So it is phi minus phi naught. This is also an isometry because it preserves the distance and it fixes origin, the special point on R2 that we can choose, which is the identity of the underlying additive transformation. Now, as soon as it fixes the origin, you can compute the norm of AX. You will see that norm of AX equal to norm of X for any point X on R2. So for XY in the Euclidean plane, you compute the inner product, it preserves that, and this proves that this A is an isometry, and it preserves the inner product. So phi of x, which is ax plus phi naught, that will also be an isometry, and this proves the result. So every isometry, every arbitrary isometry of Euclidean plane is of the form ax plus b, where a is the orthogonal transformation and b is the arbitrary point or arbitrary vector on R2. Now, in group theoretic term, there is a operation like we know what are direct products, we know what are direct products. Similarly, there is an operation between two groups which is called a semi-direct product. It's somewhat similar to the direct product, but it is not. It does not satisfy the commutativity condition that you have in direct product, right? So here, every element can be expressed as the product of two groups, but there is no other condition, and you can think of it as just concatenation of two groups, where one group can be normal to the product of the groups, All right, that's a semi-direct product. If you need more information, you just look at Wikipedia page. There is a detailed description of how semi-direct product between two groups can be think of. Now here you can identify the isometric group of E2 as semi-direct product of O2 and R2. Now O2 semi-direct product R2 is an abstract group, and we have seen that the isometry is AX plus B. So what is happening here? What really is happening here is that this group, which is a semi-direct product of two groups, is acting on E2 by this action, X goes to AX plus B. So this demonstrates the group action, even though my isometry is a transformation on the space R2, but we can identify it with an abstract group, which is semi-direct product of O2 and R2. All right. Now, after this description, we can further make it succinct by using complex numbers, because we are on a plane, so we can identify R2, a vector in R2, with the complex number x plus iy. Accordingly, the transformations ax plus b, they will convert into nice complex analytic function. Okay, not necessarily complex analytic, but nice complex valued function. Okay, so if you apply, if you identify xy to x plus iy, you will see that these Euclidean isometries will be any of these two forms in term when expressing in terms of complex numbers. This also Peter explained, Peter mentioned yesterday, and you can do it by hand in a way that I have written on the slide. So it's just a simple exercise to see that, and what you will see that you identify Euclidean plane with the complex plane, and then every isometry will be of the form either z goes to alpha z plus beta, or z goes to alpha z bar plus beta. Now, in the first case, F will preserve the orientation, so that means it will not. I mean, when a point moves along a line, it will preserve the direction. But in the other case, they are like mirror reflection, right? So they will reverse the orientation. So these are the Euclidean isometries that we obtain. Now, there is one algebraic operation that is exclusive to groups, but that essentially play a big role in geometry. That is the operation of conjugation. So you take a group G, then again I have brought yourself to an abstract group. So here G is an abstract group. Two elements G and H in capital G are conjugate if you have an element small k such that G is equal to KH, K inverse. So this is a operation which is called conjugation, and this gives you an equivalence class in the group capital G. And as soon as you have an equivalence class, you know that you can have a partition of your set capital G into disjoint union of equivalence classes. All right, so your whole group G can be divided into disjoint conjugacy classes, and each conjugacy class actually represents elements of the form HGH inverse. Now, this is an abstract definition. How does it correspond geometrically? Now, before I demonstrate how it corresponds geometrically, let me mention here that conjugation also defines an action of G onto itself. So you take G cross G to G and take the conjugation operation. That also gives you an action, and these conjugacy classes, they correspond to the orbits of the action, and I will come back to this point in a few minutes again. Now, from client's viewpoint, conjugation is just a change of viewpoint to view the same object from different corners of the house. So you are on the Euclidean plane and you are looking at objects from the Euclidean plane. Now, conjugations are like those wheels which moves your camera from one point to the other and look at the same object from a different angle. So the object does not change, but the viewing angle is changed. For example, suppose you have these grids on the plane. Okay, I have written two grids here. One is L, other is R. So L for left hand, R for right hand. Now suppose T is a symmetry of the pattern L. So we have a symmetry, so that maps this orange colored box to the green colored box. And the T is the symmetry that does it. And then you have a point, red dot, that is on the upper right box. Now you rotate your plane, the same pattern becomes the pattern on the right hand side. All right, so there is no change in your object. What you did, you just rotate. That means you just change your viewpoint. Now you know the symmetry on the left hand side, but when you rotate it, which the rotation is like your transformation S, how do you get the symmetry on the right hand side? So to do that, you have to change your viewpoint. So what you do, you stand on the right hand side, you take the reverse route along S, come to the left hand side symmetry, see how T is behaving on the left hand side, then carry that viewpoint again on the right hand side. So what you are doing, you are changing your frame of reference from right to left, and then you look how these transformations are behaving on the left hand side, and then again you are coming back to on the right hand side. So this is how conjugation works, and the transformation you travel this way is the transformation ST S inverse, and this is the symmetry of the right hand side pattern. All right, so conjugation is an important operation in geometry. Even in linear algebra, when you do conjugation, what you do? You have a vector space, you change the basis of the vector space, and you look at your linear transformation with respect to that new basis. The matrix you obtain is conjugate to your original matrix. So essentially you are doing the same thing. You are looking at a transformation from a frame of reference, and then you want to look at it from a different frame of reference. So for that, what you do, you first go to the new frame of reference. You start from the new frame of reference, you come back to your old frame of reference, see how the transformation is behaving, and you come back again to your new frame of reference. All right, and whatever you obtain that way is conjugation. So conjugation is like change of coordinate system in geometry, and it plays a big role in understanding how transformations behave, how the symmetries behave in geometry. All right, so we will now demonstrate this in our familiar domain, which is the Euclidean isometries. So we will show that conjugation, even though it is an algebraic operation, it does not change how the symmetries or the isometries behave. So the properties of the isometries will be invariant under conjugation. So based on your, if you are given an arbitrary symmetry or arbitrary transformation in a geometry and you cannot recognize it, what you will do, you will take it to your familiar frame of reference, apply it to see how it looks like. Then you see, okay, this is my familiar transformation, and then you take it back. All right. So this is how conjugation works. Now let us look at the Euclidean isometries. So suppose f of z is alpha z plus b. We know that these are all the orientation preserving isometries of the Euclidean plane. Now if beta is 0, then f of z is e to the power I theta z. You can plot it on the complex plane, and you can see that this is just the rotation. Just give me 1 minute. This phone is disturbing. Okay. All right. So we have this transformation f of z, which is e to the power I theta z, and this is just the rotation. Now, if you take alpha equal to 1 and beta not equal to 0, then f of z is just translation. You know the translations, right? They are just translations around the vector beta. Now suppose you take arbitrary transformation alpha z plus beta, where mod alpha equal to 1 because of our initial condition and beta not equal to 0. Then what sort of movement such transformations have? That it is not clear from the expression of the transformation how they look like. Now, how they look like, to do that, what we will do, we will change our frame of reference. So first note that where if alpha not equal to 1 and beta not equal to 0, then f has a fixed point. I denote that fixed point z naught equal to beta by 1 minus alpha. Then change your viewpoint by the transportation of the entire plane to a new viewpoint, which is through this translation z goes to z minus z naught. I call the new location as w. Now note that what I am doing here, I have this plane, and on the plane I have a marked point which is 0. So what I am doing here, and I have the fixed point z naught here, I am just translating in a way that my whole x-axis, y-axis, I am translating it to the point z naught, because w equal to 0 at z naught, right? So instead of choosing my origin as 0, which is the usual origin, I am just changing my origin to z naught, right? Now what I am doing from z naught, I am coming to the origin. Now I will look at how f behave at origin, and then I will come back to z naught again. So that's what conjugation means. And you see that computation here, h inverse when applied to w, it is just this function alpha w, where mod alpha equal to 1. All right. So what does it mean? That in my original frame of reference, when I change my origin from 0 to z naught, the function will just look like a rotation, and it is a rotation, all right, where the point of rotation is z naught instead of 0. All right, so you see that even this transformation looks complicated. It does not there is no you cannot visualize this transformation just by looking at the expression. But when you conjugate it, it is actually your very familiar rotation that it turns out to be. Now take this transformation, strange looking transformation, alpha z bar plus beta. Now if alpha equal to 1, beta equal to 0, we know that it is just a reflection in the real line, the mirror reflection. So your real line is the mirror and you are just taking reflection. Now when alpha equal to 1, beta not equal to 0, it is a reflection followed by a translation. Now such a transformation is called a glide reflection. Now consider if z equal to alpha z bar. Is it a rotation? I mean, alpha z was a rotation. But here again you change your frame of reference by rotating the whole plane by an angle minus theta by 2. And you see that if R inverse is when applied to this new coordinate system W, that will be equal to W bar. So even though this transformation Z goes to e to the power I theta Z bar looks like something like a rotation, it is actually a translation, it is actually a reflection, but the line of reflection is not the real line. It is a line which is at angle theta by 2 with the real line. Alright. Similarly, when you take the transformation Fz equal to alpha z bar plus beta, where alpha not equal to 1, beta not equal to 0, etc., then there can be two cases. If alpha beta bar plus beta equal to 0, then F is a reflection. Okay? And if alpha beta bar plus beta not equal to 0, then F is a glide reflection. Now to do that, you again change your frame of reference by this transformation. Z goes to, you apply rotation by minus theta by 2 to Z minus beta by 2. Okay, then you compute, you require some computation here, you can do it as an exercise. So H inverse W will be W bar plus this quantity. Now note that when alpha beta bar plus beta equal to 0, this is equal to W bar, which is a reflection, and I have already claimed that. Now when it is not equal to 0, it's a glide reflection. So this classifies how rigid motions behave on the plane. So even though the Euclidean motions, they may look complicated when you express them either in terms of complex numbers or in terms of Ax plus B, where A is orthogonal matrix. But they are movements. They are only few of them, and you can classify them in terms of 4 types. So you take any non-identity Euclidean isometry, it can be either of the following types. It can be either a translation, it can be either a rotation. In the picture I have given a rotation in angle 90 degree, but it can be rotation in any angle. It can be a reflection in a mirror line, where the mirror line can be any one-dimensional subspace of the plane, or it can be a glide reflection. That means you first reflect and then translate. All right. So these are the 4 types that is possible in Euclidean plane geometry, and there is no other type. So even though my isometric group is very big and there are many transformations, but as long as their movement on the plane is concerned, there are only four types of them other than the identity. So this is really, this gives you a better understanding of the Euclidean shapes also, because whenever you see some shape, you can try to see whether by applying one of these 4 transformations, you can make it congruent to some other shape or not. All right. And the triangles that I have shown at the beginning, they were congruent because there were all these 4 transformations involved. So there were rotation, there were reflection, and there were glide reflection as well. Or the picture, the picture that I have earlier shown here, right? These birds, this left-hand side bird, I mean, that actually is a combination of a rotation and reflection on the plane, and you get the second bird. So they are again congruent to each other. So this way, because we live in the Euclidean plane, right? I mean, our model, I mean, our analytic model of our real life is based on Euclidean geometry. So every time you see a pattern in our real life, you can try to see which one of these transformations plays a role there. Okay, so I think that concludes somewhat the overview of geometric ideas that plays a role in the overview of group theoretic machinery that plays a role in understanding geometric objects. Now, I must say here that the above classification also roughly gives you the conjugacy classes in the isometric group. I will come to it shortly. And as a comment, I would like to make here that there are also similarity transformations of the Euclidean plane where you just stretch the distance by a constant factor, and the similarity group of transformation are the scaling of the Euclidean isometry. Alright, so we can do similar analysis for Euclidean similarities also, and you will see there that the movement, there will be these 4 types, and there will be, I think, 2 more types which comes due to the stretching of the distance. Okay, so there will be stretches or stretch rotation, and then you have the stretch deflection. But I will not get into the detail of similarity transformation. I hope this already demonstrates enough how group actions or algebraic operations of groups can be used to understand geometric motions in a plane or in a geometric space. All right. So up to this, I will just take a 1 minute break, and I will like to see if there is any question. So is there any questions that I can answer at this stage?
So have you any question, participants?
Okay. So if there is no question. Yeah? No questions. Okay. So if there is no question, then I will go ahead and I will define another algebraic operation or another algebraic subset of a group which are called centralizers. So now you take a group G acting on a set X. Now for small x in capital X, when you have a group action, there are 2 subsets that you can associate to a group action. The first subset is called orbit of a point. So this is essentially the set of all points that a point moves along, right? So it's the set Gx where G is G and X is a point which is fixed. Alright. So this is the root of X along G, which is the orbit of X, and this again gives you an equivalence relation. Either 2 orbits are same or 2 orbits are disjoint to each other. So you get a partition of the set X in terms of disjoint union of orbits. And then there is an associated subgroup which is called the stabilizer subgroup. This is the subgroup consisting of all elements in the group G which fixes X. So note that the orbit is a set, but the stabilizer is a subgroup. And you can also define an equivalence relation using stabilizer subgroups. But before that, I must recall one fact that if you take the quotient group of G by the stabilizer, then G mod Gx is in bijection with the orbit of X. So when you have a transitive group action, this is like you identify G mod Gx with the set X. With the set X where X is in bijection with any of the orbits. Right? Because transitive means what? There is a single orbit of a point. So you can identify G mod Gx with the whole set. and that's another geometric speciality of group actions. Now here, as soon as you have stabilizer subgroup, you can define another equivalence relation, another relation which is the equivalence relation, and it is defined as follows: that you take any 2 points in the set X, then they are in the same orbit class if there exists, if the corresponding stabilizer subgroups are conjugate to each other. That means there exists an element small g in capital G such that Gx and Gy are conjugate by small g. So this is the equivalence relation, and this gives you another partition of the set X. All right, so what you do, well, I have not defined what is Rx here. So Rx means the set of points for which Gx is equivalent to Gy. So you take the equivalence classes under this operation, and then they give you one disjoint partition of X into subsets. So there are these 2 partitions. So when you have a group G acting on a set X, you have this partition in terms of orbits, and you have this partition in terms of orbit classes. Now you can define 2 more sets. So you can take fx prime to be the set of those points in capital X for which this stabilizer of X and Y are equal, and then you can define Wx to be a group which is the quotient group obtained by quotienting the normalizer of small x by the stabilizer subgroup at X. Now with these ingredients, Kulkarni proved a result that demonstrates how they fit in to how they might fit in to understand the geometry of X from this viewpoint. So you consider the diagonal action of Wx on G mod Gx cross Fx prime, then this map, which is the natural map from G mod Gx cross Fx prime to Rx. So you just take G, the quotient of Gx by G and comma Y, and you map it to the element Gy. This is well defined, and this induces a bijection of these fibers Rx with this set G mod. Okay, audio quality is not good. Okay. Okay, so I hope it is better now. Is it the same for everyone? Audio quality?
Yes, now it is better.
Okay. So what I am saying that you consider the diagonal action of Wx on G mod Gx cross Fx prime, then the map G mod Gx cross Fx prime to the orbit class of X that induces a bijection of the orbit class with this quotient set, which is G mod Gx cross Fx prime mod Wx. Now this is a nice theorem where you have a clear description of each of the orbit classes of X with a known object which you can deduce from group actions, and how they fit into the understanding of geometry of G on X. And that's a question that Kulkarni asked, and to some extent, I mean, it is understood how they act, how the action plays a role in understanding the geometry, but Kulkarni's idea was to specialize it in a more special setup, which is the action of G on itself by conjugation. So in that case, the stabilizers are the centralizers of X. That means elements which commutes with each other. Now, you take any two transformation in a geometry. Now, when they commute among each other, that also plays a key role in understanding the movement of the transformation. So that is where the centralizers play a role, and the orbit of Gx under this action is just the conjugacy class of G. Now, it is also known, as I have mentioned, that G mod Gx has a bijection with the orbit or the conjugacy class of G. So this theorem, if you restrict it in that setup, then it identifies these orbit classes or the conjugacy classes of centralizers with the left hand set, which is the set G mod Gx. You take its direct product with fx prime and mod it out by this group Wx. So this is a very abstract set, but that's how, in group theoretic terms, you have a bijection between these two sets. But when you look at geometrically, they may become much more simpler, as we will see now. So you back to the Euclidean isometries. Now take the orientation preserving ones. Now we know that there are these identity element, there are rotations, there are translations. Now you can prove that the conjugacy classes of orientation preserving isometries will be either of these three types. Either it will be identity, or it will be rotations where the rotation angle varies from 0 to 2 pi, or it will be translations along a real number or along the real axis. All right. So you can have translation in any direction, but all those translations can be brought back up to conjugacy to a translation along the real line. All right. So there are infinitely many of them, because any two rotations, if your rotation angles are not the same, they cannot be conjugate to each other, because that's why I have written it here in terms of matrices, because you know that two matrices, if they are conjugate, their eigenvalues must be same. But when the rotation angles are different, their eigenvalues are different, so they cannot be conjugated to each other. Similarly, you can prove the translations, they are not conjugate when you have different real numbers. So there are infinitely many conjugacy classes of isometries of the Euclidean space. So you can decompose your Euclidean space in orbits, but there are infinitely many. But when you look at the conjugacy classes of centralizers or the orbit classes, there are only three of them. It will be either identity, and then you can check that any two rotations commute to each other. So you take the union of all rotations, they will clubbed into one set, and then the set of all translations, they will clubbed into another class of the another conjugacy class of the centralizers. So even though these two rotations, they are not conjugate to each other, but when you look at their centralizers, the centralizers are actually the same in this case, but in particular they are conjugate. So this demonstrates that roughly, in this case precisely, the conjugacy classes of centralizers, they correspond to the types of the isometries that I have mentioned. So if you take any orientation preserving Euclidean isometry, you take it to be non-identity, then we have shown that there can be only two types, either translations or rotations. Now, precisely, the conjugacy classes of centralizers are also two. One consists of translations, one consists of rotations. Now, in a more complicated setup, it may not be as nice as this, but with this motivation, whenever you have a geometric space and a group of transformations in a geometry, you can ask for what are the conjugacy classes of transformations and what are the conjugacy classes of centralizers. And then by looking at the conjugacy classes of centralizers, you can try to roughly get an understanding of their movement or how they move in the geometric space. Okay, so that's how there are these two operations, conjugacy classes and centralizers. This is how they can fit into the theme of understanding a geometric space and to understand the movement of transformations in a geometric space. All right. Now, independent of geometry, this is a general question that you take your favorite group G and then you can ask for its conjugacy classes and conjugacy classes of centralizers. And then you try to parameterize the conjugacy classes of centralizers. So this is a problem which is open-ended, and for some groups it is well known, but there are many other families of groups where this question is not completely well understood, and there are many scopes of research in this direction. And as you can see that the kind of technique that you can use, either you can, if you are an algebraist, you can try to use algebraic techniques. If you like linear algebra or geometry, you can try to understand it geometrically also. But this is an open-ended question, and one can ask this for any group where it is not completely well understood. Now, one thing that I have already mentioned, that there may be infinitely many conjugacy classes, but the number of conjugacy classes of centralizers could be finite. It could be infinite also, but if it is finite, then we are in a nice situation, in an ideal situation like the Euclidean plane, and we can classify the movements by looking at the centralizers. Now, if we go from Euclidean plane to a more general space, which is the hyperbolic plane, so there also you can classify the conjugacy classes of centralizers, but there this classification does not entirely correspond to the centralizers, but roughly they classify. So that's why I have written roughly here in the top of this slide. Okay. Now there is one more issue which is of importance in geometry. That is of reversibility. So we have seen that we have seen how conjugacy classes play a role in geometry. We have seen how centralizers play a role in geometry. Now you consider, again, you come back to our well-known setup of Euclidean plane. Consider the rotations. You take rotation in angle theta and you take rotations in angle minus theta. That means you take a rotation, z goes to e to the power I theta z, and you take a rotation, z goes to e to the power minus I theta z. Now if I fix theta to be a fixed number, you look at your wall clock, and when your one hand comes from 12 to say 2, that's a rotation, right? Now my question is that, can you change your frame of reference so that these two rotations are conjugate to each other? If you look at your wall clock, you can say yes, because you just take a mirror, this rotation becomes the reverse direction in your mirror. So when you reflect, when you reflect your plane, G is conjugate to G inverse under conjugation by the reflection. But what about if you don't reflect? Well, so here, beg my pardon, so this is not Z goes to alpha Z bar, it will be Z goes to alpha Z. All right. So what about if you only consider orientation preserving isometries of the Euclidean plane? Can you conjugate a rotation to its inverse without reflecting? within the, so isometry not E2 means the identity component of the isometry group. So that means transformations of the form Z goes to alpha Z plus beta. In terms of semi-direct product, you have O2 semi-direct product R2, right? So now you take, instead of O2, you take SO2. So that will give you the identity component of the isometry group. What about there? Answer is no. Simple exercise. You try to conjugate G in matrix form to its inverse. Okay. I think this is minus cos square theta. Oh well. So I think there is a typo again. So what I have written as G inverse, it may not be its inverse, right? Or it is, yeah, because this is not determinant 1. So the minus will be somewhere else. But it's an exercise. You just try to find it out when G is conjugate to its inverse. If you do it by hand, by matrix computation, you will see that it will arise at a contradiction, and you will not be able to conjugate a rotation to its inverse within this identity component of the isometry group. All right. So you cannot reverse your rotation within the plane without keeping a mirror in it. All right. So that's why I call it reversibility. And this raises the following problem. When does a motion G is conjugate to its inverse? All right. So this is another theme of research that we shall discuss now. Okay. Now again, I still have maybe 15 minutes. Yeah. So maybe I continue and then I will stop in a few minutes. All right. So you start with an abstract group. Again, I come back to an abstract group. So I will make some definitions here. So you start with an abstract group, G, then an element small g is called real or reversible if it is conjugate to its inverse. Now I will come back to you shortly why this name real. So for the moment, let's call it reversible. Now the reflections are order 2 transformations in a geometry. All right. So such a transformation in a group is called an involution. Now, if G is a product of 2 involutions in G, it is called strongly real. You can check that a rotation is a product of 2 reflections, right? So rotations are strongly real in the whole Euclidean isometry group. And in other words, you can express a rotation as a product of 2 reflections. So some authors have used the terminology by reflection. Now, one small observation. If you have an element, small g, which is a product of 2 order 2 elements, then G is conjugate to its inverse. It's simple. You just write it nicely, you will get it. So that means every strongly reversible element is reversible. Okay? But the converse is not always true. However, if you have an involution that conjugates G to its inverse, then you can express G, then you can express G as a product of 2 involutions. So if you have a reversible element, so that the reversibility is done by order 2 element, then it is also strongly reversible. It's a product of 2 involutions. Now, how does, so other than classical G, so we have, let's now discuss origin of this notion. We have already seen one origin of the notion, which is classical Euclidean geometry, or the movement of the rigid motions. Now, you also look at some other area of mathematics, like classical mechanics. You have the movement of simple pendulum. So there also this sort of reversibility arises. Now, how does it arise? So I am not an expert in classical mechanics, but I am trying to explain it here. So you take the movement of a simple pendulum. you take the momentum, call the momentum as P, and then you denote by Q the position of the particle, and the particle has a mass m. And then there is a force that is moving your pendulum. You call K to be the constant of proportionality between the force and the distance to the origin. So I am in a three-dimensional space, so I have an origin, and I have all these quantities that is associated to the movement of a pendulum. Now, this whole movement can be expressed by a system of differential equation, system of one-order differential equation, which is dp dt equal to minus k of q, and then dq dt is just equal to p by m. If you solve this differential equation, then you will observe that if qt-pt is a solution, then so is tau of q minus t, p minus t, where tau is a function which which acts as identity on the x-axis and which maps the element on the y-axis to its negative. All right. So it's like a reflection. It's a reflection actually. Tau is a reflection, right? Yeah. So if you have a solution and you take the reflection of the solution, then that is also a solution of this system of equations. Now note that tau is a reflection, so tau square is identity, and the transformation phi, which maps your initial point to the point at 1. So you map a solution Q0 P0 to Q1 P1, then tau conjugates phi to phi inverse. So there is a reflection that conjugates the solution set to its inverse. So this is how reversibility arises in classical mechanics. That means when you have a movement of a pendulum, you can apply one transformation like a reflection so that the movement can be reversed and to it. So the movement, when it reverses, that's the inverse of the original movement. That is what this is saying. So this is one notion, one origin of reversibility other than Euclidean geometry. So there are multiple sources of mathematics where this concept of reversibility or reality comes into the picture. So in geometry, it is there, I have already demonstrated. But outside geometry, if you look at applicable areas like classical mechanics, you will see the concept of reversibility is also there. But how about abstract group theory? Well, I mean, in abstract group theory also, the notion of reversibility is implicit in the theory of finite groups. So again, I start with a finite group G. In this case, group G is finite. Now you can try to construct a group representation, which is a homomorphism from the group G to the general linear group over a suitable vector space. Then the character of this representation is just the trace of the image. And a representation phi from G to GLV is irreducible if the only invariant subspaces are either the zero set or the whole space itself. Now it's the classical result that the number of complex irreducible characters of G, that means if you take this vector space G over complex number and look at its trace, then the complex irreducible characters of G, that is equal to the number of conjugacy class of G. This is a very typical theorem in finite group theory. Now what about if you take real representations? That means if you consider representation over real numbers and try to find out an analogous theorem to this one. So this is a classical theorem of Frobenius and Suhr from 1906, that the number of real irreducible characters of a finite group G is equal to the number of real conjugacy classes in G. So that means you take the number of real irreducible characters, real valued characters which are irreducible, so their number is equal to the real conjugacy classes of G. That means conjugacy classes represented by elements whose inverse is conjugate to itself. That means conjugacy classes which contains both G and G inverse. So this is the classical theorem of Frobenius and Schur, and the study of reversibility can be studied from different viewpoints. So when a person investigates it from a group theoretic viewpoint, he calls it a real element in a group G. But when a geometer looks at it, or somebody from dynamics looks at it, he looks at an element as reversible. So that's why when G is conjugate to its inverse, we call it either real or reversible. So normally I call it real when I talk to my algebraist friend, and I call it reversible when I talk to my geometer friend. Okay, so I will go back and forth between real or reversible in the rest of the lecture, because when I speak about these elements, I sometimes mix these two notions. Sometimes I call it real, sometimes I call it reversible. So here is a statutory warning that don't confuse if I call that this element is real, and on the next slide I call the same element as reversible. They are the same. So that means real or reversible means when an element is conjugate to its inverse. Now, broad theme of research in mathematics, that you classify real and strongly real elements in your favorite group G. Now suppose your element in a group G is not strongly real. That means it's not a product of two involutions. Then find out the minimum number of involutions that is needed from G to express this element as a product of these involutions. And that number is called the involution length of a group G. Now you take a group capital G, take all elements in a group capital G, take all their involution length, and then take the supremum of all the involution lengths. So that number is called the involution length of the group capital G. So it is also a related problem to find out the involution length of capital G. So you can ask these questions for any group G. So classify real. So first of all, we have already seen how you can understand geometry of a group G by looking at the conjugacy classes or the centralizers, which are algebraic objects. But now it's a much more finer problem. So it's not about classifying conjugacy classes, but classifying conjugacy classes which contains an element G as well as its inverse. And as soon as you do that, you ask when that element is a product of two involutions from G. And if you find that, you further ask how many involutions do I need to express this element as a product of involutions. And then that gives rise to the involution length of the underlying group capital G. So these are the two related theme of research which can be asked in groups in geometry as well as abstract groups which are not in geometry, but to a broader sense, as Peter mentioned yesterday, that every group can be expressed as a geometric object. So these are geometric problems, but to understand these problems, it is not always geometric techniques that work. Sometimes you have to apply algebraic techniques, sometimes you can do it using geometric techniques. Now my time is up, so I will stop here today. Now in the next talk, I will give you some more details about some current theme of or maybe some current development of work around these three problems that is in front of you at the moment. So I will give you a survey of real and reversibility in groups in the next talk. So until then, I will stop here. Thank you.
Thank you, Krishnendu, for your nice and illuminating talk. You have broadly told the details of the acting of the conjugacy classes and group actions and all these things, and some problems also. So is there any questions from participants? So if there is no question, you just go through what he has taught today, and if you have any question, you can ask in the next day also.
Yeah.
Okay, and Krishnendu, you will send a note to us also.
Yeah, sure. I
Okay,
will
okay.
send the notes to you. Yeah.
Okay.
So I will send to you maybe in 15 minutes or so.
Okay, no problem. Okay. So thank you, Krishnendu, again. So we'll meeting again on Friday at 4 p.m.
On Friday.
Yes. Yeah.
Great.
Okay.
Thank you
you
for
now,
your
Kaushik.
attention. কি বলছো?
Now, Kaushik, you will just announce what you have.
Yeah,
Okay.
thank you. Let me first thank the speaker, Dr. Krishnendu Gongopadhyay, for his very wonderful speech, and thanks to Arindamda also for conducting this session. And we are now having around 30 minutes break, as we know. And the next speaker will be Dr. Mohali. He is from IISER Kolkata. He will deliver one talk with the stochastic processes and its applications. And I have already provided the exact title of his talk. We will again resume this particular